Good morning, here we are. Once again, it is the physics video lecture, Physics 2A video lecture 20. So, a lot of things to talk about today. We just had a quiz, and I'm going to do a review of the quiz and try to make all the comments that I had planned to make, and I already had some feedback via email. So let's put our agenda up on the board. So quiz, discussion, and review. So I'll review that. Then I also had a few homework problems, and somebody wanted to have chapter 5, number 69, and chapter 6, number 37 discussed. Thought I did this one again, but I don't mind. Talk about it anytime. And what else is on our agenda? Yes. For next quiz, give a heads up on that. That'll be the second one. And finally, pick up where we left off with collisions, and probably just end it there. I'll do one or two more homework problems on chapter 6, and we'll save chapter 7 for the next lecture. Okay. So as far as the quiz goes, technically it worked. So the system worked, the Canvas system, and that's a good thing because I can adjust the difficulty and the time and so forth. And what I'm going to do is make sure we know what's going on with each quiz, and I'll give you a heads up on how to do them. This current one had a little more material than I had intended. I had intended to have one problem with 3 parts, but the system required me to make 3 problems out of it, and so there was a bit of redundancy, and clearly would take a little more time. But that doesn't matter. It was the first one, and the fact that it functioned at all is good. So don't worry about that. We're going to do about 20 of these, and we're just collecting all the points that we can. So here's how I want to continue this quiz discussion. What I had told you in my email was that it was going to be about the vertical throw, which is what we called just the basic discussion of one-dimensional free fall. So what you wanted to do was be ready for that. So of course you had time to review that, and in particular you want to have your formulas ready. You can say you've got x equals x0 v0 t minus a half gt squared, right? That's one-dimensional free fall. The positive x direction up. V equals v0 minus gt, and v squared equals v0 squared minus 2g x minus x0. Those would be the 3 formulas that would allow you to answer any question about free fall. So that's what you would come to the quiz with, and yeah, you're going to want to be prepared because 10 minutes is not a long time, obviously. But I try to do 5 problems of this type on a typical in-class exam, and then we have 50 minutes for 5 problems. So I can adjust the difficulty and the amount of work that it'll work out for you guys. There was a handful of people who aced the thing, so I know that it was doable. Good, so you come to the quiz with this information, and you know, free fall, distance proportional to time squared is the basis of it. So now we have these 3 questions, and what was given was the maximum height. So maximum height was h. So that was given, and then we wanted to know what the initial speed was. Okay. So that's the example of using v squared equals v0 squared minus 2gx minus x0. So you're looking at that there, but we know that when we reach the top of our arc, minus 2gh, okay? That's when we reach the top, the speed is 0. There's our initial speed, v0 equals root 2gh. Okay? And only when you have this do you then plug the numbers in. And speaking of plugging numbers in, so I told the machine to be within 2% accuracy. So you do have to have enough significant figures. I can also tell the program to have 3%, 4% accuracy, but you don't need that many significant figures. You need a few. So it was 2% last time. I may bump it up to 3%, even 4%, so that you don't lose on account of that. Okay. But when you're here, then you've got 2, 9.8, and whatever the height was that the machine told you to plug in, and then you get that answer, and then you type that in, okay? Now the second one, we were also given h, but we wanted to find the speed at half height, okay? So we wanted to find the speed at 1/2 the height, and we're going to use this one again. You know, if you do use the time-dependent ones, it'll take you much more time to do the problem. So we'll use this equation again. I'm just going to write it out. But this time, to be more efficient with it and not even return to the first problem, you remind yourself that you throw something up and it comes back down, right? Throw it up and it comes back down. And so you can imagine it's the same thing as releasing it from rest up at the top, right? It comes to a stop, and let that be your initial point. Then you have v squared equals 0, because you're releasing it from rest, minus 2g, and your x minus x naught is negative 1/2 the height, because you've gone from here down to there. So if you do this, you find v squared is equal to g times h. Okay, g times h, and again you take the square root of g times h. So you have to get here in order to plug your numbers in. The third one was, what was the air time given a certain h? Okay. Given h, t sub air. Okay. Now, you can, and you actually have to use some version of this problem. But again, the best way to do it is to say it's going to be twice. T sub air is going to be twice the time it takes to fall from here down to there. Right? The time to go up and the time to fall down are symmetric, so it's going to be twice root 2g root 2h over g. Okay. Root 2h over g, and again, you have to get a function, a viable formula here, and then you can plug that in and get your answer and plug it in into the computer. Because the system in Canvas is giving you guys random numbers. Okay? Between a certain range that I choose, it just spits out some numbers for you to use. Okay, so I do admit this turned out to be more than I wanted it to be, because I wanted it to be one problem, one height, once and for all, and then the 3 problems would have been easier to solve. Okay, but that's how it's done. And so you have to review the subject when you know it's going to be coming up, and have this ready, and then go to work. What else can we say about this? Yeah, let me put a couple of notes here. So notes just in terms of our quiz discussion. Now that we've done it, you want to make sure you know these problems. So anything that comes on a quiz, make sure you really know it, because I can and will reuse a problem. Okay? I can reuse it, and so it's not like it's the last time, it's not your last chance at this problem. Okay? I could reuse one of these three parts, for a future quiz. And I intend to make them not too hard, so we'll stick with the 10-minute time frame, and I want you guys to succeed on these. So I'll tell you now what our next topic is going to be, what our next quiz topic is going to be. So, the next one, and actually I already promised it to you guys some time ago. We want to do the horizontal throw. And I won't have three separate questions this time. Try to formulate it in one. But we'll see. I'm not making any promises on that. I want it to be doable. So let's look at the horizontal throw. This is really the key thing here. We throw something from initial height h with initial speed v0, and it's understood that that's v0x, right? That's the x direction that it's being thrown in. And what happens is, like when you throw a baseball or anything like that, it ends up at a distance d from the base of where it was launched from. Okay. So what we have is this: horizontal motion is just uniform motion. Well, yeah, okay, I don't have the formulas up now. You'll do that later. Okay. I'm just going to remind you what's going on here. Horizontal motion. Vertical motion starts at h minus a half gt squared. That's the version of the kinematic equation where we change x to y and x is 0 to h. Okay. No initial speed in y direction. Okay. So you can answer pretty much any question about this right here. We can also remind ourselves that v sub x is equal to v0 as given here, but v sub y is equal to minus g times t. And when we started talking about horizontal throw, this is all we knew, okay? But then we learned about energy. So we actually also have another arrow in our quiver, as the saying goes. We can use conservation of energy, so I'll just write that down as well. So conservation of energy says we have initial kinetic energy plus initial potential energy equals final kinetic energy, which I'm just going to call V squared. But since I measure the potential energy from height 0 here, plus 0. So this is an equation that's true. And strike the mass is there. And it's another one that you can use in this scenario. So these are the relevant equations. Now let's even see what we can ask. See what we can ask about this. And the time, which I'm going to call the time in the air, or the time until the projectile impacts with the ground, that is obtained from this equation when y is equal to 0. So we get 2h divided by g square root. Okay, it's just the same time it would take to fall straight down, because the horizontal and vertical motions are independent of each other. Okay, and then the distance is v0 times this air time we found. The speed of impact we can get that in a couple of ways. We can get it from this equation, though, the easiest, or we could go into, a little more detail here. And by the way, if you do the speed of impact using these formulas and the Pythagorean theorem, of course it has to give you the same answer as this. And we can even talk about the angle of impact, and that is wrong. That's the angle that it impacts with. Okay, so I'm going to try to put something together using this scenario. This is pretty much everything about the horizontal throw. Let's see. Yeah, so that's all I'll say for now. But we're going to take, our quiz problems are going to progress through the material we've studied. And so the whole system of what we're doing, it's an ongoing review. These are all going to be important problems, right? So the vertical throw is an important one, horizontal throw is an important one. And we'll move on. After that, we may do a full-on projectile type of problem. Okay, good. So we've talked about that. And the next thing on our list, we already did these. So let's go over these two homework problems, and then we'll talk about the collisions a bit more. And then I'll assign another homework problem. Okay. So 569, that was that Atwood machine. I feel like I had done this one before, but let's look at it again. I'll just set it up. Yeah, M1 is greater mass than M2, et cetera, et cetera. So let's just set this one up first. So we have a tabletop, and we have a mass on the table, and this is M2. And it goes over a big pulley. So there's a pulley here on indicated axle. And then here's our M1, and here's a height H, okay, and here's the tabletop. So we're going to release this from rest, and it's going to go down, the other one's going to come up, okay. So this is an energy chapter, so I can call this scenario A, and B is when they pass each other at equal heights. So when it's released from rest, I just have the energy at A is M1GH. That's it. I'm going to call this my zero level. Okay? M1GH, that's the potential energy of this block. Now when they're moving, they're both moving, so I have M1 over 2 V squared plus M2 over 2 V squared. And make sure I'm answering what they want us to answer. Speed of each object. Yeah, But what's the potential energy now? So they're at equal heights. So it's M1 plus M2 total mass G times H divided by 2. So this is the energy, just potential. Over here it's kinetic of each mass, and they both have the same speed because they're connected by a string, plus the potential energy of those masses. So this is the power of the energy method. If you carefully write it down, this equation is true, and it's now just up to you to solve for V. So solve for V before plugging any numbers in. Okay. And what else? The speed at the moment this mass strikes the table is going to be set up in the same way. Okay? They're both going to have the same speed. The potential energy, so we're looking at the right side still, okay? So this stays the same. This is going to be the same. The potential energy will now be M2GH, because M1 will be down at the bottom, and this one will have the new potential energy. And finally, there was a question about how much higher does the object travel after the object hits the table. Okay, how much higher does this one travel? So this one ends up here. I'll just draw a little dotted line. Okay. So M2 ends up here, and if you can call this the y, the new y equals 0 level, then it has an initial speed, and it's really the problem we just did in our exam, on our quiz. Okay, so you're gonna have v squared equals, and I'll just call this y max, how high it goes. V squared equals v0 squared minus 2g y max. Because we call it, or y minus y sub 0. It's just going to be this difference there, what I put in here. And when it reaches the maximum height, that's 0, and then you solve for y sub max. Will be equal to v naught squared over 2g. Okay, good. So that's a great problem. Don't mind talking about it again. Okay, so the other problem that we were to talk about was 637, chapter 6, problem 37. Let's see here. This is the ballistic pendulum, so what I do on this problem is just review the ballistic pendulum. Also a great quiz question, by the way, to talk about the ballistic pendulum. So we've got this bullet coming in, m times v is its, and then m right here. If the bullet enters the block and causes the block to swing up, so its final height is h above its initial height, right? It swings up there. What were they asking in particular? Ratio, yeah. Well, the momentum after the collision is equal to the momentum before the collision. Right. This was the law of conservation of momentum. The momentum of the bullet before it collides with the block, and then equals the total mass of the bullet plus the block times the new speed. So those momenta are the same, and that ratio therefore is equal to 1. So that's because linear momentum is conserved in this collision, and the action immediately before and immediately after is happening on the level. But energy is not conserved in such a collision. Nowhere near being conserved. Okay. So momentum, I'll write here. So momentum is conserved. Energy is not. For energy, we could say the kinetic energy after divided by the kinetic energy initial. And I had done this before in a slightly different form, so let's say it is. Kinetic energy after divided by kinetic energy initial, we'll just set up that big ratio. This is 1/2 total mass V prime squared divided by 1/2 simple mass of the bullet V initial squared. Okay. So the 1/2s are gone, that's nice. Then we have M plus capital M, and the V prime is found to be MV divided by capital M plus lowercase m. So we're going to square that divided by MV squared. So now we have to do a little algebra. This one against one of these. In fact, I'll just do 2 parentheses here. So squared. So this one against one of those. V squareds are going to go away. That's nice. V squared against V squared. And we're going to end up with M numerator. One of the m's cancels against the squared one there over m plus capital M in the denominator. Anything else on that question? Yeah, that's what they wanted to know for part B. Good. So that answers those questions. Feel free to ask for any question, discussion you want from the homework, because I can always do these. And if any student wants to know these, rest assured that there's got to be 10 or 20 or 30 other students who are glad to see it being presented. So don't be shy. Okay, let's see how we're doing time-wise here. Okay, good. Now, I wanted to say something about the collisions, the billiard-style collisions. I wanted to say some general things about collisions that I didn't get around to last time. Now, I talked about cars and football players, and we showed these little cars on our track here colliding. But I have not yet emphasized that these laws are completely general, so they hold for subatomic particles that you can't see. You know, they would hold for planets colliding. Right? They'll hold at any size scale whatsoever. The conservation laws, energy and momentum, are very, very fundamental. So let me draw again our two-dimensional collision where I was talking billiards. So two-dimensional elastic collisions. I just want to draw this scenario and say a few more words about it. So we have on our x-axis, I'll just say we have M1, V1, and we're headed for a collision with our target M2. And then there's going to be what's referred to as scattering. So one of them is going to go in one direction, another one's going to go in another direction. So yeah, I've color-coded them this time, haven't I? So we can have one going this direction, then we have M1, V1 prime, and the second one here is going in this direction, and we have M2, V2 prime, so after the collision. And there are angles associated with this. I'm just calling them theta and phi. Okay. So this collision is occurring in 2 dimensions, and we're scattering in 2 angles, and we have 2 new speeds. So that's actually 4 unknowns here, for which we only have 3 equations. momentum, I'll write those right here. Momentum in X and Y. So they're on the last notes, okay? And energy equation as well, okay? So that gives us those three equations that you had in your notes last time. Now these could be subatomic particles. Next semester you'll talk about the Rutherford experiment where alpha particles were launched at gold nuclei. Okay, that's nothing that you can see. Generally, we could launch subatomic particles at some target, okay? And then these angles are measured by setting up a detector. So you set up a detector here and you detect the scattered particles and their properties. And you can imagine you swing the detector around and have a stream of incoming particles and learn about the properties of the collisions that way. So these things aren't even visible. They're just being launched with electromagnetic acceleration. What about that next semester? Launch forward. There's a target here. Things scatter off and detectors are set up. But the analysis is using these equations. Okay, the same ones we're talking about automobile collisions or billiard balls also hold true for subatomic particles. Okay, so I'm just going to write that here. Subatomic particles. When you talk about those, you're talking about electrons, neutrons, protons, nuclei of atoms, and so forth. So yeah, the generality here is very important. And you can just set up these same law equations because these conservation laws are universal. Okay, anything else on that topic? Just wanted to make sure that point is made. So next semester, you will learn about things like the Rutherford experiment, and that was, better part of a century ago. And then nowadays we have gigantic particle accelerators, biggest machines on Earth, and they're using these fundamental type of laws to understand what's going on here. So this would be the mystery zone sometimes, right? Trying to find out what's going on there. Trying to find out the properties of these things that you can't actually visualize. You can't see them, they're very small. Okay. So having said that, I'm going to assign one more interesting collision problem. Good, and then we'll call it a day. So I'll assign one more collision problem. The next lecture we start out in chapter 7. So this is an interesting one. There is a, let's see, I have to go to chapter 6 here. We're looking at problem 64. So homework 20, for lecture 20, we've got a bullet here. It's going to pass through a pendulum. We've got MV, it's going to blast through. It's not going to get stuck, it's going to blast through, but when it comes out, it has half the speed. Okay. So this is momentum conservation. The total momentum is perfectly horizontal. The total momentum is staying constant. Therefore, some of the momentum has been transferred to this capital M. So along with the momentum, it's picked up some speed, and the problem is asking you to find the speed that it would take to bring it all the way upside down. They're saying this, it's not a string, it's a massless stiff rod that'll take care of that. So it'll go up to here, just barely. So again, it's going to be a momentum and an energy conservation problem. Hope they didn't give us any numbers. No numbers anyway, okay? So it's gonna be all analytic. That's the way we like them best. So that's a fun problem to do. I think about it, maybe I should add one more. And one more. Actually, here's a very good one. So homework number 20. So this is chapter 6. What did I say? The pendulum was 664. This other one is also really good. It is another measure the speed of a bullet problem. It's 81. And for 81, let me just put a little back here. This is a perfect review problem. This time you're hitting this, shooting the bullet into the block, but it's on a table, it's resting on a table, and it's just gonna come to a stop over here. I'll draw it red where it came to a stop. It's gonna come to a stop at some distance D, or whatever they call it. I would generally call it D. Yeah, see, now you have friction. It came to a stop in a distance D. Excellent problem, okay? So you're gonna find out its initial speed, and then it's just the distance it skids to a stop. That's a problem we've done this semester. I've done that, we have it in our notes somewhere, okay? So we're just putting things together. Okay, good. We'll see you guys next time.